All right, so these first three problems are pretty similar to problems you might see on the first quiz or exam, something like that. Oftentimes I'm a big stickler about arrow pushing, meaning you need to show arrows going in the right direction, remember charges, remember everything like that. So in this first reaction, we know that the pi bond can act as a nucleophile. It will steal the proton from hydrobromic acid, and then we will get a carbocation intermediate that looks like this. All right, bromide in this case is still going to be floating around. One side question though is, what's the hybridization of that carbon with the positive charge? sp2, which means it's trigonal planar, right? So if we think about this bromide ion can attack from the top of that p orbital, or it could attack from the bottom. Both are equally likely, which means it's going to be probably a 50-50 mixture. So now we can go through and account for those two potential products. We could have one where bromine added from the top, which means that methyl group is now going to be a wedge, or sorry, a dash. And you could have one where bromine added from the bottom and the methyl group is a wedge. What's the relationship between these two now? Enantiomers. So oftentimes, instead of drawing the second one, you can just write plus En. I'm perfectly okay with that. So that can save you some time. All right, next one is pretty similar. Like I said, this can work with hydrochloric acid or hydroiodic acid as well. So we can have this attack in, kick off our chlorine leaving group. In this case, it doesn't really matter which carbon carries a positive charge because it's secondary versus secondary, and there's no way you can rearrange it, right? So now we can have our chloride floating around. This chloride can attack from either the top face or the bottom face. I'm just going to have one arrow, but we will account for both products. So for example, it could be either a wedge or a dash. Like I said, if you don't want to draw that second one, you can just write plus En. In fact, that's often what you see in the answer key in the Klein textbook as well. All right, next one's a little bit trickier though. So we've got hydrobromic acid. We're going to have this attack in, kick off our bromine. Just like we said before, you always want to create your more stable carbocation, which means our secondary carbocation is going to be favored. All right, we've got a couple options here. One option would be for our bromide to just attack directly in. And just like we saw before, this could happen from the top face or the bottom face. So I'll write plus En to indicate that that could be coming off a dash. What's the other option though? Rearrangement, exactly. So one other option would be to take one of these hydrides coming off of the ring. We could slide this over to give us a tertiary carbocation. And then we could have bromide with that negative charge attack into this carbocationic position that's tertiary. Whoops. And do we need to worry about dashes or wedges now? Why not? Yeah, it's not a stereocenter that we're creating, so there's no potential of creating an enantiomer, right? So for this one that we just did, there are three different isomeric products that you could get. So you get a set of enantiomers and then a separate one where the bromine attaches to a completely separate position. Does that make sense? All right, so let's do the next three, and I'll give you some time to work on this, and I'll pause the video while you're working through these mechanisms. All right, so the next three reactions we'll do individually one by one. So the first one, it looks like a halogenation reaction with elemental bromine. The arrow pushing for this is a little bit weird, right? So the nucleophile is going to be the pi bond. It's going to attack bromine, and then bromine's going to attack immediately right back in, and then we'll eject off bromide as a leaving group. Okay, so the key thing to remember when you're doing this one is you don't go through a carbocation. Instead, you go through this funky looking three-membered ring. What's this called? A bromonium ion. If you remember in class, I said we had a lot of experimental evidence supporting this three-membered ring over the carbocation, therefore it's the more realistic mechanism. All right, so now this bromide can attack either one of these positions. It doesn't really matter, it'll give you the exact same product, and it will slingshot open that three-membered ring. That's a good question. The reality is it could attack this carbon underneath or this carbon on top. It would give you the exact same product, so we don't really have strong evidence to support it attacking one over the other. We don't really know. We will talk about this in more detail later with ring opening reactions. We do have to pay attention to it when we have other nucleophiles involved. All right, so that's the first one. Did we have to worry about stereochemistry for this top reaction? Why not? There's no stereocenters, exactly. So if there's no stereocenters, don't worry about stereochemistry. We don't have a mixture here. We would only expect one product. All right, next reaction's pretty similar. So we'll have this pi bond attack in, bromine attack back, kick off bromide. This one we do need to worry about stereochemistry a little bit. So if we think about it, it almost forms like a little tent bromonium ion. It would look something like this. And do we need to worry about the bottom face attack? Meaning, what about the bromonium ion where the bromine's attached via dashes and not wedges? What do you think? So I'll write out what I mean. Let me draw it out this way. Are there going to be two different intermediates that we have to be concerned with? Let's think about it. Are these different or are they the same? I'd say they're the same. They're meso compounds, right? If we think about it, there's an internal plane of symmetry going through here. So this is a good example of a meso compound. The reality is we don't need to draw it twice because it's the same thing. So we'll leave that as is. And then we can have our bromide floating around still. And now it gets a little bit tricky, right? So one option would be where this bromide attacks this top position and slingshots open the bromonium ion. So I'll draw this on top. And if it's attacking that top carbon, that means that the bromine must be attacking from the underneath side, right? So if we think about it, the bromine that gets opened is still going to be a wedge, but the bromine that attacked in must have been a dash. And that means the methyl group must have flipped up to be a wedge, and then this methyl group must have still been a dash. Let me clean this up so it looks a bit nicer. I don't know if this looks much nicer, but you get the idea. The key thing with this is that this bromine's coming off a dash, that one's a wedge. That means that these are anti to one another, meaning they're on the opposite plane. Conversely, what could have happened is maybe this bromide attacked from this bottom position, and then, oh my goodness, it's doing it again. Sorry. I reinstalled OneNote today and that didn't fix it. So,
Professor, I do have a question about that though.
Yeah.
When we take the Bromonium Ion and it's attacking the pi bond that's being destroyed, and it's essentially creating two bonds with bromine.
Yep.
Are they true bonds themselves in the intermediate, or one favors the other while one is just a dipole-dipole interaction?
That's a good question. So you're getting into some nitty-gritty chemistry about the nature of the bromonium ion bonds. The reality is they're kind of in this gray area between being a true covalent bond and being an electrostatic attraction. So it's a very weak covalent bond is a good way of describing it.
So does it have like, and it's both carbons between that alkene, it's doing it with both of them, or is one bond favored over the other?
One bond tends to be favored over the other, and we'll talk more about that when we get into halohydrin reactions. Yeah, and that'll be next week.
Okay.
All right, so the other option we said was for bromide to attack this bottom carbon, slingshot this open. And if this happens, we'll get a slightly different product. It'll still be anti, but this time the bromine on the upper carbon will be a wedge. The bromine on the bottom carbon will be a dash. And you'll get these, but just like we saw before, these are still going to be considered anti to one another. What's the relationship between these? Yeah, so in this example, we would get a set of enantiomers out. Do you think this mixture would be optically active or inactive? It would be inactive, right? Because it would be a racemic mixture. Yep.
So it causes an inversion of stereocenters when the bromide attacks that cation.
Yeah, so the question was, when bromide attacks the bromonium ion, it's essentially like an SN2 reaction, so you undergo an inversion of stereochemistry, or an inversion of that stereocenter. Great question. All right, let's do the next one. The next one looks like acid catalyzed hydration. I like showing the water getting protonated first because that's far and away the most basic thing in solution. So the starting organic material isn't going to be affected at all during that first step. Now we've got our hydronium ion floating around in solution. And now our pi bond can reach out and steal a proton from that hydronium ion. All right. So now we need to consider the carbocation intermediate that we'll get. Just like before, we want to show the carbocation off of the most stable position right there. All right, so now we have water floating around. Water can attack from either the top face or the bottom face of that carbocation. So let's go ahead and consider both options. And I'm going to squeeze this down even more. So if it attacks from the top face, our water is going to be coming off a wedge. And we could have one where water is coming off a dash. All right, what's the last step going to be? Deprotonation. So we can write minus H plus. You can show the overall proton transfer if you want. So for example, if we were going to do that, we could say excess water, meaning our solvent could steal this proton, give electrons back to that oxygen. Or we could have water grab one of these protons, give electrons back to that oxygen. However, I'm okay with minus H plus at this point in the year. So we could end up with two different products for this one. All right, what's the relationship between these? They're diastereomers this time. We haven't flipped all of the stereocenters.
I have a question about the wedge in the bottom. What if you break the pi bond initially? It's still a wedge.
So on the bottom carbon right here,
Yes.
we didn't really do anything with this, so it's staying put. We're not changing the stereochemistry in that position, so we can leave it as a wedge. It's still going to be sp3 hybridized. But the reason I like showing this is students often get in this trap where they automatically assume with addition reactions that you get a mixture of enantiomers. But this is a good example of showing that's not always the case. Sometimes your mixture is going to be a set of diastereomers. So these are geometric isomers from one another. So one is cis relative to those methyl groups, the other one is trans relative to those methyl groups. So a little bit trickier there. Make sense, though? All right, the next one. is a little bit different. I want you to basically fill in the box and provide the missing reagents. So I'll give you a little bit of time to work on this one. So no mechanisms are required for this one. All right, while you're working on this, I'm going to try to give you a little bit of guidance. So if we think about the alkene here, we've got this more substituted position that I'll dot with green, and then this less substituted position that I'll dot in red right there. Which one's the Markovnikov position, green or red? Green. So Markovnikov means more substituted, red means less substituted. So it looks like in the first reaction, we're trying to do Markovnikov hydration. And in the second one, we're trying to do anti-Markovnikov hydration, right? All right, so let's try the first one. We need to do Markovnikov hydration. We have two different methods through which we can do Markovnikov hydration. The first one was acid catalyzed hydration, meaning just acid as H plus and water. Will that work in this example? What would happen, do you think? It would rearrange, right? We would form a secondary carbocation that could rearrange into a tertiary carbocation and not give the desired product in the highest possible amounts. So what do we do when we want to avoid rearrangements? Yeah, oxymercuration, demercuration. So in this example, the oxymercuration part is with mercuric acetate, which is HgOAC2. And then that forms that weird three-membered ring. We need to open that with a weak nucleophile, in this case being water. And then we get this organometallic product where we still have mercury hanging on. We need to remove mercury in the second step. That's the demercuration part. What reagent do we need for that? Sodium borohydride, which is NaBH4. I know a lot of this seems like alphabet soup of different reagents. I know I told you not to memorize things. However, flashcards for many of these do help, and I've got flashcards posted on the class website, so you can even cut those out and use those as study tools if you'd like. All right, so that would be the most appropriate set of reagents for the top one. All right, the bottom one, we're doing anti-Markovnikov. We can't do acid catalyzed hydration. We can't do oxymercuration, demercuration. What was the method we saw at the end of lecture on Thursday? Yeah, hydroboration oxidation. Some more alphabet soup. So the hydroboration part is with borane. But like I said, you can't just buy a bottle of borane. It's always tied up with some sort of ether. So you'll often see a .THF or .ET2O for diethyl ether. Either one's pretty common. So that's the first step. The second step is to use hydrogen peroxide and sodium hydroxide. This is a two-step reaction, so it's important to number each of these as step 1, separate from step 2. Students often forget those numbers. If you were just to mix all of these together into one common reaction pot, things wouldn't work right. You have to do them in sequential order. Does that make sense? All right, now the tricky one. How do we do the reverse reaction for the bottom one? This is going back to last term. It looks like an elimination reaction, but one problem I see is that alcohols are a terrible leaving group. What could we do to convert an alcohol into a good leaving group? We could tosylate it or protonate it. In this example, tosylation would probably work really well. So step 1, to tosylate it, you need tosyl chloride, which is TSCl, and you need pyridine, which is abbreviated as PYR. And then step 2, after we convert that to a good leaving group, is to use a base and do our elimination reaction. What would be a good base for this one, or does the base even matter? In this case, we only have one type of beta proton, so it doesn't matter the size of the base, right? So in this example, I would probably use some sort of, I don't know, commonly available base. We could use sodium hydride if we want. Doesn't really matter. You could use terbutoxide if you want to. Why wouldn't you want to use sodium hydroxide though? Does anybody know? Yeah, you would just substitute it back to the original starting material. Because it's a primary electrophile, it really wants to do SN2. So I would try to use a base that's non-nucleophilic here to avoid any sort of substitution chemistry. Make sense? Yeah, so there's a lot of stuff to remember from first term. It won't go away, unfortunately. All right, the next one is fill in the missing reagents for these. So they're all using the same starting material. And there may be more than one step, maybe even more than 2 steps. So you can just number them 1, 2, 3, and so on. Let's try to work through these slowly. Sometimes these look overwhelming when you're seeing them all at once. So in the first one, just like we did before, I'm just going to label each side of the alkene using a different color. So we've got the green dot and we've got the red dot. I'll do the same thing for all of these. I really like using colored pens and pencils. You're welcome to use colored pens and pencils on your homework or exams, things like that if it helps you solve some of these. So for example, on the first one, which position's Markovnikov, green or red? Green, absolutely. So in this top reaction, we need to do an anti-Markovnikov hydration. How do we do that? What reagents do we need? Yeah, BH3THF. We actually just saw that right above, right? So in this example, we're going to be using the same set of reagents. So that's step 1. Step 2 is sodium hydroxide and hydrogen peroxide. Sometimes you'll also see water thrown in there too. It's assumed that hydrogen peroxide is with some water as well. All right, the weird thing with this reaction that we didn't really have time to talk about yesterday, so I'm going to zoom in on this, is we have an assumed hydrogen coming off here, right? This assumed hydrogen is always going to be in that same position, meaning syn to the alcohol. So we didn't get to talk about that yesterday, but they're always going to be on the same face, so we call that syn addition. So the end result of this addition reaction is an alcohol that is syn to a hydrogen, but the alcohol will always be coming off of the less substituted alkene. Does that make sense? All right. Now going back out, let's skip number 2 and come back to it. That one's a bit more complicated. Let's go to the third one. All right, this one we're doing a Markovnikov hydration. What can we use for that? So acid catalyzed hydration would definitely work well for this one. So catalytic acid and water and excess would work really well for that. The other method we could use was that oxymercuration demercuration. Why would we use the oxymercuration demercuration? To avoid rearrangement reactions, right? So in this example, do we need to worry about rearrangements? No, we formed a tertiary carbocation, it's not going to rearrange. So in this example, just to avoid using toxic mercury, most chemists would use acid catalyzed hydration. All right, the next one. Looks like we're doing Markovnikov addition of bromine, so that's hydrobromination. What reagent would we need for that? HBr. What if we wanted to add the bromine off of the other position, meaning the red spot? What reagents would we need? Peroxide. In fact, let's make that an additional note. I'm just going to squeeze that in here. We can go ahead and we can say we can do a similar reaction with HBr and peroxides. Usually they're alkyl peroxides, not hydrogen peroxides. And when this happens, you'll get a mixture of 2 different products. or I should say 3 different or 4 different products. One more. So with this peroxide one, you really have no control over the stereochemistry at all. So you're not going to get syn or anti-addition. You're basically just going to scramble everything going on in that. So it is important to remember that when you have peroxides around, anti-Markovnikov addition is likely to occur. And so what I mean by that is one trick that students use is they say, up here we use peroxides and we got anti-Markovnikov addition, and down here we use peroxides and we got anti-Markovnikov addition. So that's one trick you can use to keep mental note of which side of the alkene you're adding onto. Make sense? All right. Last one here, we've got 2 bromines getting added across the double bond, and they're anti to one another. What reagent would we need? Br2. And that's it, really. All right. Do you need your laptop? Or do you need the room?
Yeah, I need the laptop.
Okay, sorry.
I wasn't wanting to interrupt you.
No, you're fine. This is just a review session.
It's kind of like, I didn't think there was a class.
No, there's not. We just found a room. All right, so the next one, I'm going to slide this over. This is going to be a multi-step reaction, and so what I might do is break it down into multiple steps. First thing I would do off of this reaction is I would try to add some sort of alkene onto this position, and so we'll try to kind of work backwards through this. And I'll show you what I mean by the alkene. So this alkene, we can go directly from that alkene to that alcohol. And how do we do that? Yeah, hydroboration oxidation. All right, so let's include that in there, and we can say, all right, we can add alcohols to alkenes. The starting alkene we would need would be BH3 THF, followed by sodium hydroxide and hydrogen peroxide. All right, now comes this weird step where our starting alkene is not the alkene that we need. But that's okay, we can make this alkene, right? So then the question is, well, what alkene should we start with? So we've got a few different options. One option is maybe we have some sort of leaving group up here, or maybe we've got some sort of leaving group right there, right? Because both of these could do E2 chemistry to give us that alkene, right? Which one do you think is probably the better choice, and why? The one on the left, why? I'd say it's easier to make from our starting material, right? If we try to go from this starting material directly to this one, that's going to take more work. So as a chemist, I don't want to do more work. I want to do the easy route, so I'll say that's too much work. However, we can go directly from our starting alkene to something that looks like that, right? What reagent would we need in order to install a leaving group in that position? HBr, absolutely. So if we did HBr, just like we saw over down here, we can install bromine right there. All right, so now the question is, what is the missing set of reagents that we need in order to get that elimination product? We need a strong base. Do we need a big base? Do we need a small base? What size base do you think we need? A big base. This looks like a Hoffman elimination reaction. What's a good big base? Yeah, terbutoxide. So you could write potassium terbutoxide. That would give you primarily your Hoffman elimination product rather than your Zaitsev elimination product. So these are the types of problems where sometimes they get kind of tricky. using a lot of scratch papered colored pencils, not being afraid of making mistakes, blacking things out, is perfectly fine. These are meant to be kind of big mental puzzles for you to work through. Make sense? All right. So we've got a couple more of these. Actually, we already did this one. I just have the last one. So provide the correct starting material for this one. This one's kind of a brain teaser. Yeah, let's provide the correct starting material and reagents. I'll give you a hint too. Focus on the stereochemistry of the bromines right now. What do you notice about them? They're syn, right? Meaning they're both wedges. They're not anti. What does that mean? When we do halogenation and try to install two bromines, they normally go anti, right? Not syn like this. And just to be thorough, I'm going to write plus En over here too. So I'll get you started with the hint. Does anybody think they have a solution for the problem of the bromines not being anti? What was that? Yeah, we could potentially have one bromine on the starting material. There's actually an even simpler answer. What do sigma bonds do? Sigma bonds can rotate, right? So let's think about this. Let's rotate the sigma bond and force the bromine to be anti, right? Students often forget about this and they get super hung up on the fact that they're not anti, and it's like, well, they can spin around in space, right? So let's think about what it would look like. So I'm just going to copy this down over here. And like we said, we can rotate this. If we rotate it like that, these are the exact same compounds, right? If we were to name them, they would have the exact same name. So in this conformation, they are anti. Okay, so sometimes you may have to consider doing a full bond rotation in order to find the correct anti-configuration. All right, so like I said in class the other day, you can consider the parent, which I'll highlight in yellow here as being static, which means that the double bond must have originally been, oh my goodness. I just got this laptop last year too. All right, so the double bond must have been in that position. So we can go ahead and we can say, all right, the double bond must have been right there, which meant that our original alkene must have been a cis alkene or a Z alkene in this example, right? In order to give us that correct final product. So sometimes you do have to consider these bond rotations. What's the reagent we need again? Yeah, just Br2. Does that make more sense? So sometimes they will throw these curveballs at you in the textbook as well. So I just wanted to give you a heads up on some of these examples. All right, were there any other questions you guys wanted to go over? Yeah. Yeah.
Find it really quick. Yeah. So it was 2-methyl-2-butene reacted with HBr over peroxide.
So 2-methyl
Uh,
2-butene
yeah.
reacting with,
HBr over peroxide.
okay,
So in this case, you would get the anti-Markovnikov,
yes.
but even with the peroxide, isn't there potential for a rearrangement?
That's a good question. So the question was, will this undergo a rearrangement? No.
Okay.
Because it doesn't go through a carbocation intermediate, it will not rearrange. We'll cover this reaction in a lot more detail when we get into radical chemistry, but it goes through a radical intermediate that doesn't do rearrangement. So if we think about it, the major product that you'll get for this will look like this, plus this, but there's no rearrangement. Does that make sense? Yeah. Any other questions? All right. Well, if you have questions over the weekend, you can always email me.
Yep.